this is one thing, but also it's many times in many applications we can derive explicit expressions for the estimators or different things using this mean squared error criterion. So we can derive explicit mathematical expressions. That's why people like it. But if you use deep learning, for example, also there, people choose performance measures that correlate better with the performance of the algorithm. You know, the performance of algorithm depends on the application. What do you want to measure? For example, suppose that you have automatic speech recognition, ASR, and you have application just like I show in the video, and you want to speak to home device. So you can measure what is the error rate, the word error rate when you speak on the average. And then for speech recognition, you can measure that, and so on, for a specific speech recognizer. And for images, you can measure different criteria, different errors on the images. It depends if it's what the purpose of the images are. For example, if the image is just to show on screen on the phone, or is it for medical applications? It's totally different performance measures. And then if you try to enhance signals for specific applications, you need, and you use deep learning. You know, with deep learning, you don't need explicit mathematical expressions for the derivations or even algorithms. You just train a network and you find the parameters. But even then, you cannot take any performance measure. Usually, in order to train the network, you need that you will be able to find derivative of the performance measure. Why do we need to find derivative of the performance measure? Do you know? Are you familiar with deep learning, or do I go? Because probably some people are familiar with deep learning, so I want to give the insight, how we use also deep learning. So for deep learning, we use training data. And then we have parameters of the network. So suppose that we have, like here, y. So it can be yt, or in the frequency domain, maybe. And then we have a network that it does something, and then the output will be zt. Or in the frequency domain, it will be the f. Usually in the frequency domain, we need all the frequencies. So this network or model, okay, so it will be a model, neural network model. It means that we have parameters. And we need to find parameters based on what? Based on training data, okay, because this is what I have. And how do I find the parameters of this model? Based on the performance measure, based on the criterion that we want to optimize. So using gradient descent, you know, when you optimize something, usually you want to do it in an efficient way because you don't have optimal solution. So you find a solution and you guess a solution, or you start from a certain point, and using gradient descent, you become closer and closer to the optimal solution. What is the optimal solution? The optimal solution of these parameters will be minimum of something, of the performance measure. For example, if you want to minimize, minimum of the performance measure that you want to minimize for the average based on the training data. Okay, so you optimize. So you find the parameters that minimize the performance measure, the average value of the performance measure, using the training data. This is what you find. But you need to do it efficiently because you don't know what are the parameters. So each time you come closer, closer. So these methods of coming closer to the solution, they are called gradient descent. If someone is not familiar with gradient descent, urgently today go read about it, okay? So it's very important. I guess graduate students, engineers, probably you are familiar, you're well familiar with that. And what are the benefits, how to optimize. Usually with gradient descent, you change also the jump, how close. Because at the beginning, you want big jumps to come closer to the optimal solution. And when you come closer, you need to decrease the step size. Okay, all of that. And if you want to learn more about it, it's with adaptive filtering, adaptive processing, and all that. So neural networks, this theory was developed for many years, decades, from the 60s of the past decade. It's not new, but now it became very popular, especially in the last 20 years. You know why? Why it became popular in the last 2 decades compared to previous years? What? Data, very good. Data, which means that we can collect a lot of data in memory. So memory is cheaper. And what else? Processing units, yes. So to process data or to find the optimal parameters of this. Sometimes these models contain millions of parameters. So think about to find the optimal values of these millions of parameters, it takes a lot of processing. So it became cheaper. Are you familiar with the first application of neural network? I think it's a massive usage. I think maybe it's one of the first application of neural network. Are you familiar with that? Which one? What do you think? When was it and what was it? When and what? Okay, the theory was much earlier, but what was one of the first applications that was very massive usage? What? ESR? No, speech recognition actually much later. Speech recognition in the last decade. Okay? What? Classification of objects. What kind of classification on which object and when? Just a minute, what? Yeah, objects in images, okay. But what kind of objects? When was it? Okay, you come close. But when do you think was it? And I tell on massive usage. Okay? Yes, number recognition, which is similar. When was it? In the 90s. 98, more specifically. Okay? In 1998. So a long time ago. And then there was a challenge, and actually it was made for usage by in the industry. So back then, for example, in the United States, people wrote numbers by handwritten numbers on envelopes. So it was zip code. And then think about to recognize the numbers. Each person writes the number differently. So what they did, and people that write the numbers, so it's possible to take a small image, maybe 32 by 32 pixels, and the numbers, which contains the numbers, the envelope. And then inside this small image, maybe 32 by 32, you have only, we can assume that the numbers are not connected. So each image like this contains a single number, single digit, which is nice. So we have classification. So we have an image, okay? So here we can have an image, let's say Y, that is 32 by 32 pixels. And the output, let's call it, this will be a neural network. And the output will be R, which is 0, 1, 2, 9. So we need to know what is the digit for handwritten digits. And think about each person, if you want to do it using some signal processing, so to take images, and an expert needs to think what are the features of the numbers, how to discriminate between this digit and another digit, and so on. So the images here are binary, which simplify things. Okay? And then it came out that for a certain neural network, actually it's quite simple, neural network, it's possible to find the features of the image, and also if you shift the digit in the image, it doesn't affect. So it's shift invariant, and then we need to classify or to find which digit it recognizes. Okay? So in addition to memory requirements, so it became easier for memory to take a large databases of many images like this for people that write different ways, different digits. And we take a large training data set that represents the whole people who wrote digits. And also computational complexity, because we need gradient descent to find the parameters of this neural network, to find the optimal, such that the classification will be more accurate. So what is the performance measure for the classification? The performance measure, what will it be? What? Okay, so we can say that this is R hat, okay? So we know for each image Y, we know the true class. What is the digit? So you suggest, so we take R minus R hat squared like this. This will be performance measure. It makes sense, right? Because this is classification error, average classification error. But this doesn't work. Actually, we want to minimize this. But this is not good. And my question is, why this is not good? What? So in terms of the application, this is a good performance measure. But I say it's not good for our problem, because in our problem we want to optimize. Does it work? Well, we want to optimize to find the optimal parameters of the network. So we need to do gradient descent. For gradient descent, we need to find derivative of the performance measure, because based on the derivative, we can come closer and closer to the optimal solution. But then because we cannot find derivative for something like that, it's not good. So just before this was in the industry, this problem, there was one of the seminal innovations that was used for deep learning was backpropagation. Okay, backpropagation that enables efficiently to train the neural network, which means to find the optimal values of the parameters, and also how to replace a performance measure with another performance measures that correlates well. Okay, so instead of finding the classification error like this, it's possible to find something like, which is close like to mean squared error, which we can find the derivative with respect to the parameters. And then we can use gradient descent. Okay, so we came from mean squared error, and I showed you that sometimes we use mean squared error, even though it's not the correct performance measure, but it enables us to find a good solution. Either which is derived based on mathematical solution, or even with deep learning, because we want to optimize the parameter, we need something that can be, we can find the derivative in an explicit expression. Okay? Okay, so you see sometimes we go out of the material, but it's important because you connect and these days this material is very important. Okay, so I recommend to study if you're not familiar with that. It's important, it will be useful for you. Okay, so here with the mean squared error, if we define the error between z and x, so you see the error is composed of two components, one that is related to the distortion and one which is related to the noise. And because the desired signal and the noise are uncorrelated, this is the assumption that here the x and v are uncorrelated. Even we can sometimes have that we can say that they are statistically independent, okay? But for this purpose, it's enough that they are uncorrelated. We have the mean squared error. We can write the mean squared error as a summation of two components, one which is based on the distortion and one which is based on the noise, just like what we had in the time domain. Now, if we have this explicit expression, you see this is the explicit expression for the MSE. So, for example, when we talk about optimal gain, like the Wiener gain, which is the Wiener filter, we just need to find derivative of this with respect to h, just like what we did in the time domain. So the derivative and equate it to 0. But in the time domain, we had to find the derivative of a scalar function of a vector. Here, it's a scalar function of a scalar, of h. H is a complex scalar. So my question is, of course it's easier. In the time domain, it was a scalar function of a real vector. And that was also useful. So if you are not familiar with derivative with respect to vectors or with respect to matrices and so on, this is also important, something important to learn. Any textbook, maybe I can send something to read, some basics. Okay, if you're not familiar, I will send you, okay? I will send some material how to do these derivatives. because it's important for signal processing, of course, array signal processing, and also for deep learning, also very important, also for image processing. It's useful everywhere in signal processing, okay? When I reach the room, I will send you today. I will look for something from textbook. Okay, but here it's even much simpler because h is a scalar. How do we find the derivative here with respect to h? Can you do it yourself? Let's wait 2 minutes. Find the derivative of jh with respect to h, because we will want to do it when we find the performance measure. Okay? And I will do it soon. How do we do it? Derivative. Okay, so I will remove the dependence on f because I don't care, but I can write like this. jh equals to 1 minus h magnitude squared phi x plus h magnitude squared phi v. And we need to find the derivative with respect to h and equate it to 0. So we need to find this derivative. How do we do that? Okay? So something I'll remind you. How do we do that? What? 2 options. 2 options. Remember that h is a complex number. J omega what? Do you want to come? Why not? Okay. So there are 2 options. One is the difficult option, one is the easier. So first, I can define h as the real number and the imaginary, hr plus j hi. And then, instead of something like this, do you agree that something like this, you think about that this is a single equation, but it's with complex numbers. So it's like 2 equations. You can take the real of this and the imaginary, and both need to be 0. So actually this is 2 equations. One for the real value, and one, when I write something complex equation equals to 0, it's 2 equations. One for the real part and one for the imaginary part. Okay? So these are 2 equations. How do I get it? So I can write djh hr equals to 0 and djh with respect to hi equals to 0. So I have these 2 equations. So I can write here, I can replace, instead of h, I can write hr plus hi, and so on, and then have these 2 equations. So if I give you time, you will be able, of course, to do it. But it's, even for this simple problem, it takes time and it's cumbersome. Alternatively, maybe I will send also some text about it to prove. I will check, okay, if I have it. So instead of this, there is an alternative way. When you have a function of a complex number, you can write it as j, h, and h complex conjugate. And then you take the derivative with respect to complex conjugate and equate it to 0. And you assume that h and complex conjugate and h are independent. Okay? This is a mathematical trick. And I will send also this, so I need to remember two things, okay? To send you some material from textbook about this. Also, it's important to know. Because this makes our life, these are two equations, right? Because complex. Complex equals to 0. These replace these two equations, which makes our life much easier. Okay, so let's do it. So we can write the DH conjugate of, let's write it as a function of H and H complex conjugate. So we can write it like this. 1 minus H multiplied with 1 minus H complex conjugate phi x plus H complex conjugate phi v. Okay? So this will be, okay, so I assume that H and H complex conjugate are independent. So I have minus 1 minus H phi x plus H phi v equal to 0, okay? So from here, I get what is H, which here it will be, okay? I will write it here. Very easy, and remember that it's generally it's a complex, but here I get for this problem a real number. So we get H phi x divided by phi x plus phi v, which in this case the solution is a real number, but I didn't make that assumption. Just I found the derivative and equated to 0. So if you try to work with these two equations, you will see that even for this simple problem, it takes much longer time and effort to do that. So this trick, which can be proved mathematically that it works, and it's important to read why we can do that. Either you read it on textbook, or maybe I will find some material, you know, maybe 2 pages. It's important to read this stuff to understand why we can do that, because it's beyond that, complex numbers. Any questions so far? Okay, let's continue. Okay. So also for the mean squared error, we have 2 different definitions. One is the narrow band, and one is the broadband. And the broadband MSE, somehow, okay, I'll work from here somewhere. Okay, and the broadband MSE, this is the narrow band MSE, just like we said, this is the definition. And we can also have the broadband MSE, which is simply the integral. Where is that? Here. This is the broadband MSE. So it's the integral of the narrowband MSE. Because the mean squared error, we find what is the mean squared error for each frequency, and we take the integral over all frequencies. So if we find H for each frequency independently that minimizes the narrowband MSE, necessarily the vector H that we found will minimize the broadband MSE, obviously, okay? So what we find here, it also minimizes the broadband MSE, because we can work on each frequency according to our model. We work on each frequency independently, and then the broadband MSC is an integral of the narrowband MSC. So if we minimize each one individually, and of course each term of the MSC is positive number, so if we minimize this integral, we minimize the total integral, okay, obviously. And also the broadband MSC is a summation of two components, one which is associated with the distortion and one that is associated with the residual noise. Somehow it doesn't work. We'll, after the break, we'll try to fix it. Okay. Any questions? So we define performance measures. Now we can find the optimal gains. So the optimal gains, the Wiener filter, we just worked on that. So we can find it also from here, which is the derivative using the expectation. Also we can find it from here. And then we have the Wiener filter that goes like this. Okay, this is an alternative way, which is also a way to work on that. How do we work on that from here? Okay, so I will show you an alternative. Instead of this, what is the mean squared error, JH? We can say that JH is the expectation of the error, which is HY minus X magnitude squared. Okay, here we found it as a function of variance of X and variance of V. But we can work directly from here, from the definition. Also it's fine. Okay, so if we open that and we write Y equals to X plus V, we get this one. But we can work from here. And now, if we want to find the derivative of this with respect to H, we need to write it as separately as H and H complex conjugate, which is HY minus X multiply with complex conjugate of H, Y minus X. Okay? So if I take this derivative of J, H, H complex conjugate with respect to H complex conjugate, we have it only here. So it will become as expectation, okay, the derivative goes inside of, let's write it like this, Y complex conjugate multiply with H Y minus X. And we equate this to 0. Okay, so this is what we have. And then if we put it inside, so we have H variance of Y, because this and this variance of Y equals to cross variance or covariance between X and Y. And if we, so we can find that H is the covariance of X and Y divided by phi Y, which is the same as this. Why? Because Y is equals to X plus V, and V is independent of X, so they don't correlate, so it becomes like variance of X. This is the numerator, and the denominator, which is phi Y, variance of Y, which is the summation. So we get the same solution. So we get the Wiener filter. So this is the Wiener gain, which is the input SNR divided by 1 plus input SNR. So remember when we ask about that when the input SNR increases, we want to have higher. So if the gain is between 0 and 1, we want when the input SNR is higher, it means that we want to keep the signal undistorted in those frequency bands. For frequencies when the signal narrowband input SNR is high, we want H, the gain in those frequencies, to be higher or closer to 1. When the input SNR in frequencies, the narrowband input SNR is low, H will become lower, closer to 0. So we see that the Wiener filter behaves like that, which makes sense. If it didn't behave like that, then something is wrong. Then it doesn't make sense. Okay? Okay, so we can write the Wiener filter also using the magnitude squared coherence function. So I will define it immediately in the next slide, but before that, magnitude squared coherence function, it means how x and y are correlate. How do they correlate? So if x and y correlate, high correlation, it means that the input SNR is high. So you see that the Wiener gain is simply the magnitude squared coherence function between x and y. And it's 1 minus the magnitude squared coherence between v and y. Okay? So if v and y have low coherence, it means that the noise is low. So the input SNR is high. It is the same. So it's also possible using this relation. And the definition of the magnitude squared coherence function, if you remove the magnitude squared, so this is the coherence function. So it's actually correlation between two samples, complex samples. So we take x, y conjugate, complex conjugate, and we normalize it by the variance. And also we can do it for the noise, how it looks like. So these expressions are easy to obtain. Okay. We can also define something which is nice. You see, the coherence function is a real number, right? So we can define a complex coherence function between x and v. And this complex number, we can define it as the coherence between x and y plus j, the coherence between v and y. So we can write this, so you know that this is the magnitude of this, the magnitude squared of this, plus the magnitude squared of this equals to 1. Under our model that, you know, this is the model. So since this is the model. So in our case, since this, the magnitude squared of x and y, plus the magnitude squared of v and y equals to 1, we can define an angle, which we call it theta for each frequency, such that we define theta such that this will be cosine theta, and this will be sine theta. It's allowed. Why? Because the magnitude squared of this plus magnitude squared of this is 1, so we can define theta such that theta is between 0 and 90 degrees. Okay? So we can define theta between 0 and 90 degrees, pi over 2, such that theta is defined such that cosine theta for frequency, certain frequency, narrowband, equals to coherence between x and y. Okay, so this this value, the magnitude of this, is between 0 and 1. But also we know that their summation, this summation is 1 because this is our model. Okay? Why do we need it? So the way we need it is the definition. Okay, we can define this theta, but also for when we want to represent signals, sometimes we represent signals as vectors. So suppose that we have a vector, x. This is the desired signal. And the noise is uncorrelated with the signal. So it means that the noise is like this. I can write it like this. This is the noise. It's uncorrelated. So we have here 90 degrees. When we have two vectors uncorrelated, so signals, we say that they are uncorrelated, so we have 90 degrees between them. And then we can represent their summation, y, x plus v, and this is the angle, theta. Okay? So this says, this represents how x and y correlate. So what is the angle between the desired signal and the noisy signal? So it's just like graphical representation of signals. And you can represent signals this way. It's more like a convention. So when theta is small, we see that y and x are more correlated. When theta is large, it means that they are less correlated. Also, we see that when theta is small, the noise is small. So the input SNR is high. When theta is large, closer to 90 degrees, we see that the noise is large. So the input SNR is lower. So it's a nice way to present signals this way. So we can write also the Wiener filter using this convention and parameter. So we can write it that h, the Wiener filter, we can write it as cosine squared of theta, which is 1 minus sinus squared of theta, using this definition of theta. Okay, so I can ask you, what is the definition of theta, and to represent it in a graphical way for signals like that. So if the noise and the desired signals correlate, we can also define. So it will not be 90 degrees. It will be some angle between them. Okay? And then we have summation. So it's a nice way to visualize dependence or correlations between signals. Okay? And then we see that if theta goes to 0, okay, it goes to 0, what does it mean? That the input SNR is very high. It goes to 0. So the noise is small. So it goes to 0. And h of cosine squared theta goes to 1. And when theta goes to 90 degrees, the SNR, so cosine squared, goes to 0. So it's a nice way to show it. And also we can see some examples like this. We can also present the MSE and see some relations, and we can also write the other performance measures, the noise reduction factor, the desired signal reduction factor, and the distortion index as a function of theta, which is nice to show. It's a more compact way to present it. And also we can plot the Wiener gain as a function of the input SNR. So this is the plot. You see when the input SNR increases, it becomes closer to 1. When it decreases, it becomes closer to 0. We can also plot theta as a function of the input SNR. You see, when the input SNR is high, which means that V is small, theta goes to 0. Theta goes to 0. When the input SNR is low, it goes to 90 degrees, pi over 2. Okay? And we can also plot the noise reduction factor, the narrow band, as a function of the input SNR, and the distortion index as a function of the input SNR. See, when the input SNR increases, using the Wiener gain, the distortion decreases. And a nice property that we obtain the Wiener based on the MSE, the narrow band MSE. And then I can ask you, what will happen with the broadband output SNR? So it can be shown that the output, broadband output SNR is not smaller, it's always larger or at least equal to the input SNR. So the Wiener, just like we know in the time domain, so the Wiener gain, always we can get some, at least 0 gain in broadband SNR. And there is a proof for that, okay? I will not go into the details, but here is the proof. We will take 10 minutes break. I will talk about specific example and using the Wiener gains to enhance signals with certain spectrum. Okay. Any questions? Okay, so now it's like 11:13. Let's have 10 minutes break. It's tea break, right?